How's it going, everybody, and welcome back to another 1001 MSc online tutorial video. My name is Brock Grant, and today we're going to be covering some questions regarding kinematics in one dimension. So prerequisite for this module, of course, is the Kinematics in One Dimension video 1, the one preceding this video. Now, another prerequisite is to make sure that you are comfortable with maths, because these next few modules are going to be very math heavy. So prioritizing that in your study will be highly important. Now, I do recommend that you go through the questions in your lecture notes first, as that will help sort of warm you up and help you build up to these types of questions here. So let's push into it. So the first one is on page 65, question 9. So the big thing here with this question is being able to interpret it, being able to understand, okay, here's the question. What are we being asked? What are we being given? What's the link? So we know that we have a tourist that's being chased down by an angry bear. Very good. It's running in a straight line towards his car at a speed at 4.0 meters per second. Okay, the car is at a distance d away. The bear is 26 meters behind the tourist and is running at 6 meters per second. So the tourist reaches the car safely. What is the maximum possible value for D? Okay, so a couple of things here. One, I recommend whenever you're doing a physics problem like this to draw a diagram, because it allows you to visually see what you have and what you need to find. So here is our lovely diagram here. Don't judge me too hard on my drawing ability. So we can see here we've sort of included all the information that was given to us in this paragraph here, and we know what we need to find, and that is D. So something we need to do here, we need to look at this question, and there is a brief assumption that we need to make. So what essentially this question is saying is, what is the maximum possible distance that the tourist can be away from the bear? So imagine, if you will, he's running for his life, the bear's chasing him, but don't get too bogged down in the details. Don't sort of go, oh, it's going to take him 0.2 of a second to open the door handle and any of that. Just imagine that as soon as he touches the car, he's safe. Okay? The bear goes, oh, all right, and walks off. So that means that the time, so how long it takes for the tourist to get there, is going to be the same as the time for the bear. So with this assumption in mind, we can now look at what we're given and how can we work with this. So we want D, we want this D distance. We're given a speed, and we've just seen here that our time is going to be the same. So we can go, now if you rearrange this, that will give us, and this is the main formula that we want, as we're going to use it to substitute this equation together, and I'll explain what that means in just a moment. So our next step, what we need to do is, because we see here that the time for the bear and time for the tourist and time for the bear are going to be the same, we know that their distance and speed is going to be the same. So what we can do is we can substitute this as, for the bear is going to equal for the tourist. So this means that we can have our distance. So we're going to have, for the bear, its distance was 26 meters plus D, because we've got 26 plus D gives us his total distance traveled, over speed. So he was going at 6 meters per second. Is going to equal to, so the tourist distance, which is distance D, over the tourist speed, which is 4 meters per second. So what we do now is we rearrange this equation. Okay, so we've just rearranged our equation now, so it's a little bit easier to interpret. So what we can see here is that I've had to put this in brackets because this is addition. So we need to place those within brackets. So our next step is we expand these brackets. So we go 4 times 26 is going to give us 104. Plus 4 times D is 4D is equal to 6D. So we can see we've got our addition here. So we rearrange this. So we're going to move our 4D over. So that's going to give us 104 is equal to 6 minus 4, which is going to be 2D. Now the operation here between the 2 and D is a multiply. So we're going to move this 2 over here. So it's going to be 104 divided by 2 is equal to D. So this means that D is equal to 52 meters. And all this says is that the maximum possible distance that that car could be for the tourist to reach it alive is 52 meters. So if it was 52.1 meters, he's gone, he's gobbled up, he is dinner, okay? If he was 51 meters, he's safe. And so using that sort of deduction is so important with modules like this. Being able to really look into the question, understand it, and look and see these links like, oh, time for the bear and the tourist will be the same. So how do you develop that sort of skill? Practice, 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 practice. And in time, you'll nail it. Okay, let us look at the next one. So a jetliner traveling northward is landing with a speed of 69 meters per second. Once the jet touches down, it has 750 meters of runway in which to reduce its speed to 6.1 meters per second. So compute the average acceleration. So it's asking for two things here. It wants the magnitude and the direction. So the big thing here is that we are given a direction, so northward. So this tells me that we're looking at vectors. So we're going to be looking at our kinematic equations, so velocity, displacement, everything like that. So we know that we have the initial velocity, 750 meters. So we have our displacement, which is 750 meters. We have our final velocity is 6.1 meters per second. And we want the acceleration. So I've got 3 of our 5 values. That's brilliant. So you look at your kinematic equation sheet and you go, well, okay, which one has all of the things that I need? And the very important thing to note here is that there is only one formula that does not involve time, which is where not any point here has time been mentioned. So we know that the formula that we must need to use is v squared plus vo squared plus 2ax. So what I'm going to do here is I'm going to rearrange this formula so that we have isolated our acceleration, which is what we're wanting to calculate. So now that we've rearranged our formula here, this is the one that we want to use, we simply plug and chug. We go v squared. So our v squared was, so we had 6.1 squared minus vo squared. So pop those in brackets. Divided by 2 times x. So x was 750 meters. So now we plug this into our calculator. So we go 6.1 squared is going to give us 37.21 minus 4761. There, so we've sort of simplified it a little bit. We now take 37.21 minus 4,761 in brackets and then divide it by 1,500. So once we do this, so we should get an answer of negative 3.15 meters per second squared. So what does this mean exactly? It means that the plane is decelerating at a rate of 3.15 meters per second squared. Okay, so let us look at the next one, which is question 35. So 2 knights on horseback start from rest 88 meters apart and ride directly towards each other to do battle. Okay, so they're wanting to sort of charge each other like jousting. So Sir George's acceleration has a magnitude, so that's how much, of 0.3 meters per second squared. So 0.3. While Sir Alfred has a magnitude of 0.2 meters per second squared. So relative to Sir George's starting point, where do the knights collide? So they're both charging towards each other. Whereabouts do they clash? Now, a very important word here is relative. So what relative means is from that person's point of view, from their perspective. So for example, if you were walking along the street and you saw a car zoom by, from your perspective, that car was going very fast. Whereas from the car's perspective, you were going slowly. So what we do here is we need to acknowledge, okay, what do we have? And there are two assumptions that we need to make. So the first assumption is that the time for both of these people, so for George and Alfred charging each other, are going to be the same. Why? Because they're both going to hit. So it means their time is going to equal. So we know that the time for George is going to equal the time for Alfred. The second assumption that we can make is that we look at our total displacement. So we know that both of these two are going to run a certain distance, which we don't know, that's what the question is asking us, but we know the combination of how far George runs and how far Alfred runs is going to equal to 88, because they need to clash, they need to hit. So we now know that if we add both of their displacements together, we will get 88 meters. And with that, we can now start this problem. So the first equation that we need to use is that we are looking primarily at acceleration here. That is our main motive. So we look in our formula list and we sort of see a bit of a problem. None of them really fit. Now, I'm going to show you how we can get around that in just a moment. But for this question, I use the formula here. So we look at, we'll do George first. We'll do George. So the displacement for George is VOT. So we ask ourselves, okay, what is George's initial velocity? And it is 0 because he's starting at rest. So we know we have 0 times t, because we don't know time, plus 1/2 a, we know is 0.3 meters per second squared, times t squared. So we can further simplify this and go, okay, so 0 times t is going to be 0, and 1/2 at squared. So we know that 1/2 of 0.3 is going to be 0.15 t squared. Now this is a slight problem here because we go, well, hang on, we've got two unknowns. How are we supposed to solve this? And I'm going to come to that in just a moment. So I'm going to put a little square around this because that's going to tell me I want to come back to that. So now we're going to look at the total displacement for Alfred. So the displacement for Alfred is VOT, so it'll be 0 times t plus 1/2 a, which is 0.2 meters per second squared, times t squared. So by simplifying this, we go 0 times t is going to be 0. 1/2 of 2 is 1, t squared. So the displacement for Alfred is 0.1 t squared. That is our displacement for Alfred, but we sort of have the same problem, and that is we don't have all of the variables. What are we supposed to do? Here is where we look at our assumptions that we made over here. So we know that if we add both of these together, we're going to get 88 meters. So XA plus XG is going to equal to 88. So we can substitute that with what we've written here. So we can go the displacement for George, which is 0.15 t squared, plus the displacement for Alfred, which was 0.1 t squared is equal to 88 meters. Now, the next assumption comes into play here, because I can hear you guys going, well, hang on, well, what are we supposed to do with these variables here? We know that t time is going to be the same for both people. So what it means is this t here is the exact same as this t here. They're one and the same, they're identical. So it means we can just simply add them together. So we can get 0.25 t squared is equal to 88 meters. So we see here we have a multiplication between the 0.25 and t. So t squared is equal to 88 divided by 0.25, which will give us 352. So we know that t squared is equal to 352. Now, as we've done throughout simplifying this whole time, where the opposite to a multiply is a divide, and opposite to an addition is a subtraction. The opposite to an exponent, which is this, is going to be the square root. Okay? So that means we're going to have t is equal to the square root of 352. So if we punch that into our calculator, we get 18.8 seconds. What this means is it's going to take 18.8 seconds for these two people to clash. Now, we look back at our original question and we go, okay, so relative to Sir George's starting point, where do the knights collide? So it's all well and good that we've gone, oh yes, both of them put together is 88 meters, but we want to know how far George traveled. Now, the big thing here is what was holding us back at the very beginning. Over here, what held us back is that we didn't have both variables. We didn't have x or t. But by doing it this way, we've just calculated what t is. So now we can use this formula to calculate the displacement of George. So we go, so the displacement of George is equal to 0.15 t squared. So displacement is 0.15 18.8 squared. So we know that 18.8 squared is going to be 352 because we're just doing the opposite of what we did here. So that means the displacement is going to be 0.15 multiplied by 352, which means that the displacement for George is going to equal to 52.8 meters. So relative from their starting points, so relative to here, and from George's point of view, when they said 3, 2, 1, go, George travelled 52.8 meters from his starting point, and it was there that they collided with Alfred. So that would be about about here, roughly. Okay, so let us look at the next one. So, a locomotive. So, why not they just say car, but anyway. A locomotive is accelerating at 1.6 meters per second squared. So it's accelerating at 1.6 meters per second squared. It passes through a 20-meter wide crossing. Okay, so he's passing through this crossing in a time of 2.4 seconds. So after the locomotive leaves the crossing, how much time is required until the speed reaches 32 meters per second? Okay, this is a really tricky one because it's involving more than one situation. We can't just use one formula, away we go. We need to break this into chunks. We've got a before, middle, and after. So the first thing we need to do is we need to investigate and go, okay, we know the locomotives, we know its acceleration, we know the displacement of this one. Okay, so we know that the crossing is 20 meters, and we know that it passed through this in 2.4 seconds. So what we do here is we need to look at how fast was this car going in the beginning, because it didn't say at rest. So we need to look and calculate how fast the car was going initially. So how we do that is we look at the change in overall displacement using acceleration. So that formula is x equals VOT plus 1/2 AT squared. So the displacement is going to be 20 meters is equal to VOT, so the initial velocity, we don't know, but we know that the time was 2.4 seconds, plus 1/2. Now the acceleration we know is 1.6 meters per second squared, times 2.4. So what we're doing here is we're using a lot of the information about when the car was in the crossing to find out what happened when the car was out here before the crossing. Okay? So what we do is we do a bit of rearranging here. So what I did here was I went 2.4 squared, then I multiplied that by 1.6 and then divided it by 2. So again, we rearrange this. So we've got our addition over here. So we move that through. So that's going to be a subtraction. So 20 minus 4.608. And we can see here, this is a multiply. So that's going to turn into a divide. So we've got divided by 2.4 is equal to VO. So the initial velocity is equal to 6.4 meters per second. Now this is very important because now we know how quickly the car was entering in here, which means we'll be able to calculate how quickly the car will be leaving in here. So how we do that? We don't use this formula anymore. We use a slightly different one. We're going to use, so what we do is we have our initial velocity here. So how quickly is the car going to be entering this crossing? And we want to calculate how fast will the car be going when it leaves. So the final velocity, we don't know, is equal to the initial velocity. So the car entered at 6.4 meters per second, plus, so the car was accelerating at 1.6 meters per second squared, times 2.4 seconds. So what we do here is we multiply these two together. So we've got 2.4 multiplied by 1.6, and then we add 6.4 to that. So that will give us a final velocity of 10.25 meters per second. So what this told us is we now know how quickly this car left the crossing. Now we can use this information to calculate how long it will take from the car from this point here to reach this point over here. So our final step is we go V equals VO plus AT. Now, this is where things slightly change because our initial velocity is now 10.25 because we're looking at the car starting here and finishing here. Whereas with this part, question 2, we were looking at it starting here and finishing here. So things change around a little bit. So our final velocity is 32 meters per second. So 32 is equal to our initial, which is 10.25, plus our acceleration was 1.6 meters per second squared, because remember, with these types of questions, it is the acceleration must be constant. And we multiply it by time, which we don't know. So we see here this here is an addition. So we're going to move this over. So it's going to be 32 minus 10.25. is equal to 1.6t. So we're going to have 32 minus 10.25. So that's going to give us 21.75 meters per second is equal to 1.6t. So this is a multiply, so that will turn into a divide. 1.6 will give us t. So this means that t is equal to 14 seconds. Okay, so this one was a tricky one because it involved multiple sections. And again, this is where I really need to reinforce that deep understanding. As long as you understand it, you'll be just fine.